If you have one of these nifty clamp multimeters, you can easily find out the power usage of any of your electrical devices and how much it costs to operate them. For example, this desk lamp. If I plug it into the extension cord and turn on the multimeter to amps with the symbol A on it, I should be able to see an electrical current flow for this lamp. But if I clamp it around the lamp wire, it does not show any current flow, as if there is nothing going on there, but I can clearly see that the lamp is on and working, and clamping around the extension cord is not any better. But if I remove the insulation from the extension cord and separate wires like so, clamp it around a single white wire, and I can suddenly see some electrons flowing through that wire. The white wire is typically a neutral, and the black one is typically a hot line wire. Clamping around it will show exactly the same amount of electrons flow, but in opposite direction from the white wire. The green one is typically a ground wire, and you should not see any activity there, because it's just for your protection and not for regular use. Going back to the neutral side. Depending on how you hold the clamp around the wire, it will show you slightly different results. This is not the most accurate way to measure the current flow, but is very convenient and can give you a good general idea of your power consumption. For example, knowing that the power outlet is 120 volts AC here in United States, I can multiply that by the amperage of 0.33 amps equals 39.6 watts, almost 40. And that's exactly what is stamped on the bulb, 40 watts. And that's great. But how about if you want to measure something that doesn't have a wattage stamp on it, like an iPad for example? I have two chargers for it. One is a regular iPhone charger, and the second is a dedicated iPad charger, so we can see the difference between them. And if I clamp around the charging wire, I get absolutely nothing. But clamping around the neutral or the hot wire shows me the current flow of 0.06, which is a very low power consumption. And if I move the charging cord to the iPad charger, which is more powerful, I can see right away that the current flow more than doubled, which means it uses more power and charges faster. To find out exactly how much power and how much it costs you, you can easily calculate it. 120 volts multiplying by 0.15 amps equals 18 watts. Now multiply 18 watts by 365 days a year, assuming that you charge it every single day, 1 hour a day. I get 6570 watts, but since utility companies charge by the kilowatt, I need to divide it by 1000. And the result is 6.57 kilowatt hours. Here in Florida we pay 12 cents per kilowatt, so multiply it by 0.12 and I get a whopping 78 cents. Wow, that means I pay less than $1 to charge this iPad for the whole year. But this is obviously a low power consumption device. How about something that requires more power, like a hair dryer? When I switch it to the low setting, it moves about 3.2 amps of current. And when I switch it to the higher setting, the current increases more than 4 times. And if you want to do a quick calculation how much power that is, multiply 13.7 by 120 volts. And the result is over 1600 watts of power is being used right now, multiplied by 365 days a year, again assuming that you use it every single day, divided by 1000, and that's 604 kilowatts, multiplied by 12 cents per kilowatt, and the result is $72 a year. An electric tea kettle also requires a lot of power, but I guess not as much as that hair dryer on a higher setting. This kettle pulls 8.46 amps. How about this television set and the cable box together? I plug them into that extension cord and I get 3.1, 3.2 amps. But this is a plasma TV and requires more power than LED TV. Now I will turn the TV off, but leave the cable box on just to see the difference in the current flow. With the TV off, the current has almost disappeared. So obviously most of the power is used by the television. To measure the current flow of these Christmas lights, I don't even have to plug it into this extension cord with split wires, because the wires on Christmas lights are conveniently split into power and neutral. Most home appliances use an alternating current, which means the current flows from power line to neutral wire in an instant, turns around, and flows right back from neutral wire back to power. And the cycle of changing direction back and forth happens 60 times per second, really fast. This is called frequency, and it's measured in hertz, as on the label. While in United States the frequency is 60 times per second, in Europe and other places it's 50 times per second, so it's 50 hertz. I can measure just one direction of the current, and if I clamp both wires at the same time, the opposite directions of the current will cancel each other out, and I would not be able to see any activity there. And the last thing I want to check is this electric oven set to broil. Give it a few seconds, and the current flow of this oven on broil setting is about 7 amps at 60 Hz frequency. Now let's change the setting to a toaster, and the current flow almost doubled at about 12 amps. And if I clamp around the neutral wire, the current flow would be exactly the same at about 12 amps. And with such a high current flow, even if I don't clamp around the wire, I can still detect some of the electromagnetic waves produced by the high current. I hope this video was interesting for you. If so, please share it with your friends, subscribe, and also hit the like button. Thank you.